So today we're going to talk about orbital diagrams. There's got to be a better way to do what we're doing. This is just too complicated. There are too many little circles, too many drawings. Let's try and make this a little bit easier. I'm going to give you an orbital diagram. And how do we determine which orbital an electron is going to be in? An S, a P, a D, or an F? Well, I'm going to use some orbital diagrams that are empty. And I'll show you how I create them later. But bottom line is I want to be able to give you an empty orbital diagram and see what we can do with it. Now we have to be able to fill it. The problem is to fill it we need some special rules. And I need to spell them out so that you're sure of what they are. So please make sure you write them down. And write down what they are. Okay? And these are all things that we've already demonstrated. So you've already seen them, but we're now putting them down in writing. The first rule is called the off-bow principle. And the off-bow principle says electrons are added one at a time to the lowest energy orbitals available until all the electrons of the atom have been accounted for. In other words, when I add an electron for hydrogen, I'm adding it to the first S energy level. I don't stick it in the third one. I don't stick it in a P energy level or a D energy level. I put it in the lowest S orbital level because that's where it belongs. That's the off-bow principle. Okay? So when I put in an electron, I'm never going to put in an electron up here. I'm going to put my first electron down here. All right? Because that's my 1s level. Now, when I put electrons in, electrons behave as if they're spinning on their own axis. They're really not, but that's the way they behave. So we call them, because we can relate to this, it's something that we can envision, even though it's not really what's going on. We can envision a clockwise or a counterclockwise spin. So spin is important in determining how electrons are arranged in atoms. So if I want to put in the first electron down here in the 1s level, and then I want to put the second electron right here in the 1s level, I have to have some way to identify that they're spinning differently. Okay? I could write something up, but the easiest way that we chemists have found to do is to create an arrow going up for the first electron and an arrow going down for the second electron. The first arrow indicates the spin going up and the second one indicates the spin going down. They are in opposite spins. Okay? That's what this says. So, the Pauli exclusion principle says that each orbital in an atom can hold at most 2 electrons. Can't put 3 in there, only 2. And these electrons must have opposite spins so that they are paired. So when I put the first one in, and I'm going to be real lazy, I'm only going to draw a half arrow going up and a half arrow going down. So when I put them in, I must put them in with opposite spins. Okay? I want to put in the third electron for lithium, the fourth electron for beryllium. They have to be opposite spins. I could even put in the fifth electron for boron. Alright, so it should be clear that the capacity of an atomic orbital to hold is a maximum to hold 2 electrons. We already determined that. And that capacity determines the maximum number of electrons allowed in each energy level and each sublevel. Let's look at Hund's rule. Hund's rule says electrons occupy equal energy orbitals so that a maximum number of unpaired electrons exist. It's easier to demonstrate that than to try to explain it. Electrons will go in individually before they double up. So let's look at the p orbitals. If we are looking for hydrogen, hydrogen has 1 electron. Right? So that electron is going to go here. Helium has 2. Lithium has 3. Well, we can only put 2 electrons on any one of these lines. Okay? So that means we have to put number 3 up here, and then we put number 4 up here. Now, why do we put number 4 not up there? Well, because off-bow says we start at the bottom. Now, what's next? The 5th electron. The 5th electron would be for boron, and it would go here. Now, the 6th electron, Hund's rule says you can't put the 6th electron next to the 5th one because it really doesn't want to be close to it. Remember when we drew our p orbitals? We said we have a p orbital that kind of looks like this. We put an electron in it, but we don't want to put the second electron in there because it would rather be further away. So we'll put it in this guy over here. Right? So we demonstrate that by saying this is like the p orbital in the x direction, this is the p orbital in the y direction, and this is the p orbital in the z direction. So we'll stick an electron there for carbon. And let's say that we are putting in nitrogen. We're trying to put in a 7th electron. We'd put it in over here, and that would be the one that's coming out of the board at us. And we put an electron in there. So we always separate them when we can, so long as we are at the same energy level. But once we pass that, for example, here we have a total of 7 electrons. Let's say we want to put in 8 electrons. If you want to put in 8 electrons, you have to put an electron in one of these things. It doesn't matter which one it is. Typically, by convention, we will put it in this one, and the spin must be different. Until we come down that way. All right, so let's draw the orbital diagram for hydrogen. Our rules say we start at the bottom. Spins must be opposite, although we only have 1 electron. Could you have it facing down? Sure. Right, but convention has us facing it up. So that's our orbital diagram for hydrogen, 1 electron. Orbital diagram for helium. Helium has 2 electrons. We start at the bottom, and we put them in opposite spins. Lithium. Lithium has 3 electrons. Well, there's 1. There's 2. Now, the third one cannot go at this level, right, because we're told there can only be 2 electrons per level, and they must have opposite spins. So that means we have to go to our next level. We're still working our way up from the bottom. That's a total of 3 electrons. That's the electron configuration for lithium. When we go on to beryllium, beryllium has everything lithium has, but then has 1 extra electron. Well, we don't have any more like we have in the p orbitals. We don't have any more spaces over here. So we have to just stick the 4th electron right next to the 3rd one. Boron's the interesting one where we have that extra 5th electron. There's 1, there's 2, there's 3, there's 4. We've already described that. And your 5th electron is going to go here. Now remember, when we add a 6th one, it is going to go in the next spot. Let's do carbon. 1, 2, 3, 4, 5, 6. By the way, how do I know there's 6 electrons in carbon? Well, because there's 6 protons, because that's carbon's atomic number. So when you look at your periodic table, and guys, if you are not looking at your periodic table, pause the video, get it out, make sure you're looking at your periodic table. All right, nitrogen is number 7. 1, 2, 3, 4, 5, 6, 7. We're good. Okay, 7 electrons, because we have 7 protons. The fun one is now coming after this, which is oxygen. Oxygen is 8. So it's really easy to do the first few. 1, 2, 3, 4, 5, 6, 7. Now what happens? Well, that 8th electron, we can't go up a level because these guys aren't full yet. So we have to start doubling up just like we did on our 1s and 2s. That's oxygen. And how about fluorine? 1, 2, 3, 4, 5, 6, 7, 8, 9. Still have 1 free. Well, that's going to be neon. Neon has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, just I'm going to digress for a minute. What do you notice has happened? All the lines up to this point are full. Notice we are done with everything that says 2. We are done with the 2s and the 2p. Right? If we were doing the same thing at the 3p, we would notice that we could end right there and have these guys all full, and something would happen. And the same thing at the 4p. What do I happen to notice that this is? Well, this is neon. It's a noble gas. I wonder what it would be if we went up there. Interesting question. All right. Orbital diagram for sodium. You try it. See if you can do it. Pause the video. Go give it a shot. All right. We have to put in 11 electrons. So there's number 1. There's number 2. Opposite spins, Pauli exclusion. There's number 3. There's number 4. I can move up because of off-bow. I start at the bottom. Okay. Hund's rule says that's 4, 5, 6, 7. I split things up at the same energy level until I must double up. That's 8, 9, 10, and there's 11. And I have 11 electrons in sodium because I have 11 protons. All right. So what do I notice about hydrogen? Hydrogen has one electron there. All right, so just kind of remember that. That's hydrogen. Lithium, everything is full up to here. That's 3. How about sodium? Sodium has 11. 4, 5, 6, 7, 8, 9, 10, 11. Oh, look at that. It has a single electron in an s orbital. This one had one electron. Hydrogen had one electron in the 1s. Lithium had one electron in the 2s. And sodium had one electron in the 3s. Isn't it interesting that they're all very, very similar? And as a result, they're all right above each other in the periodic table. Isn't that interesting? Yeah, we'll talk about that some more in the next podcast. But I'd like you to try sulfur. See if you can go ahead and do it. Pause the video. Try to do sulfur. Okay, when you looked at sulfur, did you see that sulfur had 16 electrons because it had 16 protons? So we have to work our way up. So here's 1, 2, 3, 4. Remember to separate them. 5, 6, 7, 8, 9, 10, 11, 12. Those are the only things at that level. 13, 14, 15, 16. Okay. 16. Yep, that's good. Okay, so that's sulfur. How about calcium? Give it a shot. Pause the video, try it on your own. Alright, calcium's number 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Whoops, that's wrong. 19, 20. Okay? And that's my 20. That makes sense. Alright, try nickel. This is the harder one. Right, nickel has 28. Pause the video, give it a shot. Alright, 28, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, nickel has 28. 1, 2. Now notice we're in the B block. 3, 4, 5, 6, 7, 8. There's a lot more room. Okay. Alright. Titanium. Go ahead and pause the videos. Try that one. Alright, titanium is number 22. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There's titanium. That's an arrow. That is not a 1. Okay, we're good? Alright, you try bromine. Okay, welcome back. I'm going to do the end of it. The end of bromine is going to look like this. 1, 2, 3, 4, 5. Right? Everything else down below it, right? All these down here, they all have 2 things down there. How do I know that? Bromine has 35. Let's see. There are 2 here, 2 here, 6 there. That's a total of 10. 2 here, 6 here, 2 here. That's a total of 20. There are 10 here. That's a total of 30. There are 5 electrons showing up there. That's a total of 35. This all makes sense. Alright, so given an empty orbital diagram, you should be able to fill it in appropriately for any balanced atom. Given a completed orbital diagram, be able to tell what the balanced atom it represents. So let's look at this one for a minute. How can I tell what it represents? I simply have to count arrows. Well, I'll get 2 arrows, 2 more, 6, 2 more, 6, 2 more, and up here I've got 2. So let's add the whole thing together. 2 plus 2 is 4, plus 6 is 10. Plus 2 plus 6 plus 2 is 20. Plus 2 more is 22. Is titanium number 22? It certainly is. That's the way I can check that. Alright, know how to apply the Othel principle? Know what it is. Same thing for quality exclusion. And same thing for Hund's rule. If you didn't write it down, go back and watch the first 5 minutes of the video, because that's where it is. Right? Any questions? I'll see you in class. Have a great day. Bye.